Welcome to today's OneLIMS webinar. It is great to have you all here. My name is Philipp Osterwalder, and I'm the CEO and co-founder of OneLIMS. At OneLIMS, we believe that digitalization only creates value if it connects systems, people, and data, and that in a meaningful and sustainable way. That's why we bring together voices from the field, people who understand the reality of production floors, lab benches, and control rooms. Today's session is all about challenges many of us face on a daily basis. So how we can transform individual expertise and tribal knowledge into systems that learn and evolve. And to help us exploring this, I'm really thrilled to welcome someone who's not only walked this place, but also helped shape it. So welcome to today's session, Matt Suter, CEO of Enblex.
Hi, hello everybody.
Great to have you here today. Before we start, a quick housekeeping rules. So today's session is being recorded. You can drop your questions directly in the chat at any time. So we will have a Q&A session at the end. We'll take as many questions as we can in the live session and answer the rest by mail. The slides we shown are also available on the presentation from Matt as well on request. If there is anything you'd like to explore further, feel free to contact us directly at hello@onelims.com. I also put together, as always in the OneLIMS webinar session, some goals for today. And let me start with to have why tribal knowledge, your operational instinct and experience is still invisible backbone of production. Another one is where the real gaps lies between data, processes, and people, and why dashboards alone won't fix that problem. How to turn analytical lab data into practical processes parameters. This is also an important thing. And we have another one is what neural networks can do in manufacturing and what they can't. So where are the borders of the possibilities? And the last one, how to build systems that don't just execute, but also involve. So it's not about replacing people with AI, it's more about amplifying human expertise with smart systems. My goal today is also to give you a framework to rethink how your knowledge flows from people through data into systems. And I'm pretty sure Matt will also guide us through. Okay, introduction to Matt, the speaker today. Because before we begin today's session, I'd like to introduce our guest speaker who brings a rare combination of scientific depth and operational pragmatism into visionary thinking. So Matt Suter began his journey in food engineering at the Zurich University of Applied Science, where he specialized in process informatics. He was driven by a clear idea to bridge the world of data analytics with process control, turning raw data into concrete machine settings that improve production outcomes. His early research took him to Massey University in New Zealand, where he explored the dietary fibers affected starch functionality and nutritional impact. A project that seamlessly connected lab results, ingredient behavior, and process design and health outcomes. In industry, he started at Velchlin, one of Switzerland's most renowned B2B chocolate manufacturer. There he worked in R&D, developing tailor-made chocolate products, and deepening his understanding of how raw materials, properties, product data, and machine behaviors convert in the real world. Scaling these insights across production environments further shaping the ability to align analytics with manufacturing reality. To strengthen this bridge between data and production, Matt pursued a Master's of Engineering in Computational Physics, where he focused on thermal modeling of data that derive practical insights for process design. At the same time, in his role as quality and technology manager, he built and optimized lab operations, quality systems, and process control workflows, always with a strong focus on integration, collaboration across teams, suppliers, and customer interfaces. His experiences grew with significant automation and investing projects, notably the planning and realization of highly automated production sites like for Oro de Cacao, built around the patented cold extraction cacao process. Matt then added to his portfolio by driving deep into AI and machine learning and ethical hacking, equipped himself with the tools to bring advanced intelligence and secure connectivity into industrial systems. Today, as a founder and CEO of Enblex and a member of the expert chamber and specialized group Artificial Intelligence of Swiss Engineering, he helps manufacturers, investors, and craft producers turn complexity into clarity, means transforming data into insights and insights into performance. What sets Matt apart is his interdisciplinary fluency. He speaks a language of machines, materials, data, factories, and people, and knows how to connect them into current, scalable, and future-ready systems. So, nothing to say. Please join me and welcome today's speaker, Matt Suter.
Thank you very much, Philip, for the invitation to this webinar and the warm introduction.
Welcome.
I will now, just a moment, I will share my screen. So hope you can see my slides now.
Yes, I can see it. Perfect.
Okay. So the topic today we are diving into connects two essential worlds. On one side, we have data and digital transformation, sensors, digital tools, and AI that are shaping how we run operations today. On the other side, we have the hidden but essential human knowledge and expertise that drives production decisions every day. And today's challenge and also opportunity is to connect both. So I'm quite excited to take you on to this journey. And yes, let's explore together how we can connect data, process, and human knowledge to create operations that are adaptive, real world, and future ready. So let's start with the big picture. In manufacturing, we operate across multiple domains. We have raw materials, labs, lab analytics. We have production machinery, but also factory, building, and utilities, and also the energies to run the processes. And everything is set up to achieve a high quality product that meets the product that the customer wants. But in the center of that all, we see the human. People, workers, technicians, engineers, and operators. And of course, effective operations depend on how well these domains work together. But the real challenge lies in translating and applying information across these domains so that the peoples and labs and the machine systems can make decisions based on shared understanding. Raw materials are one of the key drivers of the need for synchronization. The composition of raw materials and the behavior can vary from batch to batch, from supplier to supplier, and also depending on origin and harvest. But our customers expect every product to be consistent, same taste, same texture, and same quality every time. So we are quite forced to control and stabilize our output and, of course, prevent inconsistent results, instability, and inefficiencies. But with the variability of our raw materials and dynamic processing environment, it's difficult to achieve that level of consistency. But why is this still so difficult? Not because we are lacking tools, but because we are lacking connection. The ability to link, adapt, and apply information between raw materials, labs, machines, and peoples. So that's why today we will focus on how to align these domains, how to extract the right information, connect it such that people and systems can use it. So we will focus on the lab. Let's shine the spotlight on the lab first. The first place where raw materials reveal their secrets, their real properties. Incoming raw materials, ingredients for our recipes, are tested in the lab under controlled conditions. But we don't just measure. We create the first real opportunity to detect variability. And also, we build the foundation for production control. But the challenge, how can we adapt lab insights to real production processes? We need to know how to respond on the production machine when an ingredient behaves differently in a mixture. Or we have to know how to adjust the recipe or the machine accordingly. So from the data we get in the lab, we are always looking for relationships and information to link raw material properties directly to production machine settings. And in an ideal, perfect world, the adaptation would be very simple. So if we have ingredients with more moisture, we have to apply more drying in production. Or if another ingredient leads to a thicker product in a mixer, then probably we have to slow down the mixing speed of the stirrer. But we all know the real world is not that simple and processes are more complex. So ingredients interact and often behave differentially in production. And individual lab values very often don't directly predict production behavior. Often too many factors interact and interactions are involved. The missing links of adapting lab data to productions are costly. These missing links lead to inconsistent products, troubleshooting, rework, and often a trial and error approach. So to overcome this, we need to account for complexity, variability, and non-linearity. And we also have to consider shifting process dynamics and context-specific dependencies. We need structured and digitalized lab data, because only then lab data become a powerful source for uncovering meaningful indicators, especially when combined with other information and production data. So let's take a step forward. When lab data alone isn't enough to give the full picture. In this, production depends on something much more and direct and practical. Something that quietly keeps many factories running. So we deep on tribal knowledge. The experience, the intuition, and the hands-on adjustments made by people, the tribal knowledge, the practical, experience-based knowledge that often lives inside people's heads. Like operators who slow down the machine when summer temperature rises, not because a sensor told, because they have seen what happens if they don't. Or another operator who adjusts the process just by looking at the texture and knows it's right just by its feel and experience. These small adjustments are what's compensating for raw material variability and the dynamics of machines and the interplay with environment in production every day. And many factories nowadays wouldn't run without this kind of knowledge. It's the living foundation of operations built over years of hands-on experience. It has been accumulated over time, sometimes passed on, sometimes not, sometimes written down, mostly not. And when experienced people leave or retire, this knowledge often disappears with these people. So this is why capturing operators' knowledge early is so important. And true digitalization doesn't start only with data and sensors. It also starts with people and their experience. So our goal is not to replace this knowledge, but to understand it, structure it, and integrate it. Only then we can build systems that truly support us, supporting in keeping consistent product quality, supporting in making close and effect relationships, and to enable automation also in areas that are too complex and too fast or too risky to leave to human guesswork. So let's take a step forward to the formalization of tribal knowledge. Practical know-how and experience has always shaped how we operate, long before data, dashboards, or artificial intelligence. Even in the Stone Age, people knew how to make fire. They understood you need wood, you need oxygen, you need a spark, like an ignition source. And they also learned that the fire goes off if it rains or it will not burn with wet woods. So people related fire and experienced that fire caused light, heat, and smoke. They learned how to use heat for cooking, drying, and metal melting. which gave us techniques that have been very important in the Iron and Bronze Age. But people also found alternatives to drying, the sterilization, by canning food and applying heat, which was introduced in the very early stage of the industrial age. So before we go forward and jump into the digital and data age or AI age, we want to go another step further and to see how we could apply structured tribal knowledge in practice. So let's have a look on a practical case in the from the food industry, where we have doughs for baking, chocolate mass for refining, or protein mixtures for meat alternatives to be extruded. The texture often changes slightly from batch to batch. Often this is driven by variability of raw materials, and all these variabilities are having an effect on machine parameters like baking, mixing, cooling, and drying. So if you want to ask an operator if the material that has to be processed, a dough, a chocolate mass, or a protein mixture, is soft, and our operator has only the options yes or no, 1 or 0, then we lose some kind of details that's needed for the fine-tuning of the machines. And that's why, of course, we need something more flexible than just yes or no. So what's the alternative? And that's exactly where fuzzy logic comes in. Fuzzy logic, introduced already 60 years ago, allows us to describe the reality in a way that's much closer to how people actually think or speak. The word fuzzy simply means something that is not sharply defined. And instead of forcing the operator to say yes or no for the judgment of a mass to be produced, we can express conditions in more natural terms like very much, little, very less, or something in between. So fuzzy logic is designed to handle imprecise measurements and blurry impressions and the uncertainty that comes with real-world materials and conditions. But how fuzzy become usable in production? The core idea is simple and powerful. We define if-then rules, just like an experienced worker or operator would. Let's take the example of controlling a mixer. Let's say we want to adjust the stir speed based on the temperature of a mass or the consistency of a dough, as we have fuzzy classified in the previous slide. Or the moisture of an ingredient could be a judgment of an operator as well, or a lab value. So we build up rules based on human knowledge. For example, if the temperature in the mixer is high and the consistency of the mass is crumbly, then we know from experience, then we have to speed up the mixer. And so we end up to combine and to make logics and together our knowledge, to include our knowledge in a model. And the result, the model gives out of the knowledge-based rules by, of course, by mathematical computation behind, is that we need, for example, a steering speed of 2,500 RPM when we have this temperature, this consistency, or that moisture of an ingredient as an input. And for those who that is too complicated, look at modern washing machines. Modern washing machines mostly have fuzzy logic control inside. So we input how much we load into the machine, how dirty our clothes are, what kind of fabric our clothes are, and also the desired water temperature. And by fuzzy logic, the machine itself outputs the target wash cycle, spin speed, water level, or the rinse intensity. And if you are curious to explore this further, check out the web for examples provided at the bottom of the slide. The egg boiling fuzzy logic robot or the tipping problem, which are both great examples of fuzzy logic in action. So let's jump now to the data age and also, of course, AI. The traditional programming that we applied so far was hard-coded rules. So we applied rules to process the input to a desired result. But nowadays, once we have more and more data and AI, this is different. We learn our neural networks and machine learning models by providing tables and hundreds and thousands of data sets with historical data, with inputs and results to learn our models. So the model from the input and output develops some rules looking for pattern relationships. But this is all very nice, and these models are quite powerful and find patterns and relationship that we human not are able to discover. But the weakness, if there are some input parameters or some important parameters are missing in the model is not accurate and giving wrong outputs. So we need to do something else, to do it some robust, to improve. So we have to ask ourselves, how can we fill those data gaps? How can we prevent that we have missing data in such models? So we need to watch out for meaningfuls and missing signals. But how to find the missing signals in production? So, of course, we have lab data that also analyze raw material properties, but usually, as we have seen, it's not enough to only try to link lab data to the machine settings in production. So we have to look out for sensors inline measurements and signals from motors, valves, and actors. So let's say we have, or we are producing a product that starts liquid and solidifies in a mixer. And to stop the process, the mixing process, in the right moment where the red dashed line is just before turning to solid, what do we do to control that? So if we take a sample out of the mixer and bring it to the lab, probably we lose much time and we are too late to stop the process. So let's go closer to the machinery and take a sample and analyze it at line. But as well, we lose some time. So we have to watch out for inline signals, online signals, and yes, the traditional way, through a hole, we look into the process by human eye and decide on when to stop the process. But this is very subjective and not consistent, judging just visually by human eyes. So we look for cameras, or if we can get an important signal out of the motors, of the electric current that also increases with increasing viscosity. Or the temperature that also controls how the vessel is being cooled or heated. The characteristic of cooling or heating could also tell what the viscosity of the mass right now is. And usually, and not very obvious, we have the chance to also detect or measure the pressure at the beginning and at the end of a pipe and see if we have a pressure difference. The thicker the materials is, the harder the product will flow, and also influencing the pressure difference. So we see we have a lot of hidden signals that, in combination with lab results, lab data, and so on, could help us in giving us the full picture. So to summarize and to connect everything, people, process, and data, it all starts with people first, their knowledge, experience, and the logic they have developed through years, and based on observation and production insights. So we have seen that knowledge can be captured and structured, for example, using knowledge graphs that map relationships, rules, and dependencies. This makes knowledge transparent and formalized and ready to be used, and used for control systems, and nowadays, of course, also in AI models. Our processes, machines, lab methods, and sensors generate a lot of data that can help us to monitor, control, and improve, but we need structure, formalization, and to bring the data in a digital form. And knowledge, and sometimes creativity, to find the right and relevant data, like we have seen for looking for hidden process signals that indirectly could tell us more about the process. But raw data alone is not enough. We need data analysis, data engineering, we need statistics, and we have to look for correlations and signals that matter, and to filter out what isn't relevant. Only after that, AI comes into play, not as black box solution, but as a structured and explainable system grounded in real world context. And this is exactly the direction of today's neurosymbolic AI, where human knowledge, logic, and domain expertise are combined with neural models to create AI that's not just powerful, but trustworthy and context aware. So we have enormous potential in our operations, and with the right mindset, knowledge, data, methods, and tools, we can unlock it and to build the foundation for systems that combine human knowledge with AI efficiency. Yes, we have to make sense of data by extracting the right data, connect it with lab, process, and human knowledge. And let's unlock also the potential for adaptive and future-ready operation. So we are already approaching the end of the session, but we still have some time for your question. And yeah, there will be so much more to explore, but I hope my presentation inspired and showed how much untapped potential lies when connecting data process and human knowledge. And I'm happy to continue the conversation, whether now in the Q&A or afterwards. And you will find my contact details and Q&R code to connect right here. So thank you for your attention. And with that, Philip, I hand over to you to open the space for questions and reflections.
Thanks very much, Matt. I'm very impressed and kind of speechless, impressed, related to the information and the topics and the insights and experiences you shared related to core challenges or adapting lab data and production, structured tribal knowledge, fuzzy logic, even that I didn't have any idea before. So you clarified a lot of my questions already within the presentation, but still there are crazy more questions that you triggered in me. And I want to start and open the Q&A session with the first one is how to differentiate or distinguish between truly valuable tribal knowledge and legacy habits that hindered innovation. How do you approach that?
Yeah, that's a good question and very relevant, because in factories we have different teams, and different teams and people have different ways of doing the same thing. Mm-hmm. And often it's hard to tell what really works and what not, and also what's worth capturing. But we can distinguish what's worth capturing often by the results, because we build knowledge itself and produce consistent and reliable results. Mm-hmm. So if it can be explained by data, logic, or fundamentals, then it's likely worth to capture. Mm-hmm. But if it's done, and we see it very often, if it's done only because we always do it like this and we don't have an explanation, then probably it's just a habit. And in that case, we have to ask question, we have to challenge for explanation, and we have to find out what truly helps.
That makes sense to me. That's want to go further with another question from Danny, who's joined today. And Danny wants to know, for which kind of products can these processes be used? And where are the limits?
Yes, so I focused very much in my presentation with use cases in the food industry, but we can adapt the concept to other industries as well, and not only industries. It's how to represent and formalize knowledge. So we see it every day now, where AI agents coming up, and it's all about of reasoning and formulation of rules as well. So I don't think that there are much limits in terms of where we can adapt that concept. By creating or making these knowledge graphs, ontologies, how we call it. Just if we keep it by itself and we don't combine it with other tools like AI, then probably it's quite limited and brittle. We need also the computational power of neural networks, but if we combine them, both of them, then we have a powerful tool.
You mentioned a very important point related to the expert knowledge and how you can make sure that this expert knowledge is not biased when you're going to turn it into the system or the rules by transforming. Before you're transforming, you have to make sure or make clear that this information is truly valuable and it's correct.
Yeah, so it's like in any case, dealing or when formalizing something, when creating models or formalizing knowledge. So it's all the same, we have to be critical. Because if we carry some biased information or assumptions onto some formalization, then we include these errors in our models as well. And what works for one maybe is not working for another. So it's like training models. If we learn it with wrong or noisy data, the models not generalize in new situations and make wrong decisions and predictions. So how to prevent that when it comes to expert knowledge? We have to discuss it in a team. Beyond our domains, all the people involved in that operation, decisions, and we have to challenge openly and to include other perspectives as well. And in operation and production, in the field of production, if we are unsure, then usually we ask the process and test it on the machines.
Yeah, trial and error. Kind of. Yeah. Also the challenge internally related to the operations or the procedures, kind of to recognize the patterns is a very good point. And also it leads to another questions that arise, is that can you describe a moment when a gut feeling from an operator kind of outperformed a model? Do you experience?
Yeah, so the nowadays models are pretty good, and the chess computer wins against human, but so when it comes to the point when gut feeling wins over or outperforms over a model, then usually it is the case where a model is based or applied on a case which is more complex and where more data and cause and effect are around. So I remember the situation in a production machine where all sensors were within the specification, and the control logic of the machine was not raising some errors or something. But operators working from day to day at the production line, they have seen that the product showed some separation. And later we find out that the humidity of the environment, which was not part of the model, leads to the point that the control logic, the model, was not detecting the error. So this was definitely a case where the gut feeling that something is not right, and even if we have everything in digital and controls around, then that there is something, some other parameters around that influences the decisions.
Mm-hmm. Got it. Great example related to the experience. So want to close the session nearly, and to go ahead with the last question is, if you look ahead 5 to 10 years, it's kind of far away, but what kind of role will human process intuition still play in a world of self-optimizing systems?
Yeah, this is a key topic, and it's also related to digital transformation and the role the human plays in digital transformation. So when we shift from intuition to structured knowledge, so yes, we have to work on that, as we have seen in that presentation, that we have to formalize knowledge and intuition to become explainable and shareable and grounded in logic. And yes, human insights will stay essential to guide and to question models, and also to give context to improve the models. So I think the future systems will be smart through data, of course, but also stronger through knowledge.
Mm-hmm. This in combination will be the leverage then.
Yes, of course. And this is exactly what we can see with all the terms and the disciplines of AI. It's not only neural networks, it's a fusion of combining physical laws or knowledge with our model. But at the very base of that, the rules and the knowledge that we are able to infuse to that model. So the human will be an important part in that.
Thank you very much for your feedback and also answering all of these questions. If you have even more questions, then let us know in the chat or send directly to Matt. Connect with Matt through LinkedIn and send him directly your questions. Matt will be happy to share knowledge, insights, and also collaborate. So thank you all for joining us today. I hope this session gave you practical ideas, new perspective, and a bit of inspiration to rethink how your organization learns in these days, all about tribal knowledge. And skip back to the goals slide in this presentation and tick all the goals that we covered today. If you found a gap, send also Matt an email with a request, and we'll figure out how we can put up a second session to dig deeper into specific topics about tribal knowledge and get into more insights in the use cases. So special thanks to Matt for sharing your insights and experiences and for your time. For more information, feedback, follow-ups, reach out anytime at hello@onelimbs.com, or as mentioned before, connect with Matt and write him directly. So let's keep building systems that don't just run, but grow. So have a great rest of the day. Take care and happy lab work. See you soon. Bye-bye.
Thank you. Bye.